What was the instrument?
Violin.
Violin. And then it was the Heisenberg uncertainty principle, the de Broglie wavelength. I think those were all the questions. Was that all the questions? That was it? Okay, yep. So we'll go over what all that stuff means. What it was about. All right. So it starts off in section. That was bigger. Oh, cool. I can. All right. So it starts off in section 3.5. In the previous sections, we were talking about electromagnetic radiation. So we were talking about light. And now in this section, they're talking about electrons. And they're saying that electrons have the same properties as light. Did I misspell Heisenberg on the quiz? I was doing it at like 1 o'clock in the morning. Oh, on the whiteboard. Okay. It's like, gosh, I don't know what I'm doing. Okay. So one thing they don't talk about in the book, which I wish they would, is more about the waves. And so with the waves, if you're standing on the beach and you have one wave come up toward you, it's just like it's a wave. Let's see, clarify, 3.5 was talking about how do we get the equation, but can understand the wavelengths. Yeah, okay. I'll talk about it. All right, so what happens if you have two waves like this come in together? If they hit each other just right, they kind of cancel each other out. But then if they hit each other just right, they make like a bigger wave. And it's the same thing when it comes to light waves and electron waves. And they did this experiment. It was called the narrow slit experiment. So they had something, it was tiny, tiny, tiny. I've seen these before. When you look at them, they're like, gosh, they look just like wire, kind of like wire grating or something. You can't really see through them. And so if you do a light experiment, so you have some, I don't know why I'm drawing a light bulb like this. You have, okay, let me draw the light bulb again. You have, I'm not sure that was better. Anyway, so you have a light bulb and it's shining light. And then on the other side, you have an index card. And on the index card, what happens is you would expect it just to be light on the other side of the index card, but it's not. It's actually light, dark, light, dark, light, dark, light, dark, light, dark, light, dark. And what's happening is you get two waves that join together to make a brighter spot. And in the blank spots or the dark spots, you get two waves that destroy each other. And so that experiment is the one they did to say, oh, it's behaving more like waves, because you're getting kind of waves coming out this way and waves coming out this way. And so it's kind of is producing this light-dark pattern. But when they had a source, an electron source, and they did a very similar experiment, then they had the same thing happen. They had like electrons, no electrons, electrons, no electrons, electrons, no electrons, and so forth. So there were like blank areas, and they were like, oh, that's cool, it behaves just like light. So doing this experiment, they were like, oh, electrons are like waves. And so before, they had said, okay, so we have the nucleus, and we have these orbits, and the electrons are like planets. And so they thought that, you'd be like, okay, so the electron is like there. But then what de Broglie said was, instead of a circle around it, what you get is like a circular wave. And that's like the worst circular wave anybody ever drew. but it's like a circular wave that goes all the way around it. And that's why the electrons are behaving like waves. So and also the electrons behave kind of like particles as well, because when you have the photoelectric effect, where you have metal and then you have a light source coming in, and if it's the right amount of energy, it will eject an electron. So it's saying that light is coming in like a packet of light, hitting the metal, and then ejecting an electron. And in that case, it's more like billiard balls hitting each other. So they're behaving like particles. So what they call that is wave-particle duality. And that's where something behaves as both a wave and a particle. And the book, it kept referring to them as, I think it was calling them matter waves, which I think was more for to help you understand it than to really give you a good definition of what it's called. But it's just saying that light behaves like waves, light behaves like particles. And it's the same thing with electrons. And then de Broglie also had this bizarre idea that everything behaves like a wave. Like, you behave like a wave, I behave like a wave, my calculator behaves like a wave, clouds behave like waves, dirt behaves like waves, light behaves like waves, electrons are like waves. And then so you're like, yeah, I behave like a wave. And so it's like, what? Is this guy completely out of his head? And to some degree, I kind of I don't think he's out of his head so much as he's like, oh, I found a formula. It works. And so he was like, okay, I'm going to explain that by saying everything's a wave. So here's his formula. It's called the formula for the de Broglie wavelength. This is how you spell de Broglie. So it's the de Broglie wavelength formula. This is definitely a formula you want to memorize. And it's wavelength equals h. Exactly, I think you are. That is very true. Okay, mu. Now, depending on what book you're looking at, you might also see it like this, with a z. I think in this book they're not doing the z because we have nu, and nu looks like this, and that's for frequency, so they're trying not to confuse you. So they use a u instead. The u is oddly enough for velocity, or speed. How fast is something going? How fast is the wavelength for the particle? And then this is the mass. And it's super, super, super important that the mass is in kilograms. Otherwise, the whole thing will give you a crazy answer. And then this is still Planck's constant. And if you looked at my notes carefully last time, I think it was the second class that I went over my notes in, they realized that I had made a Frankenstein number in there. I wrote that Planck's constant was 6.022 times 10 to the negative 34. That's not true. This part goes with, exactly, this part goes with Planck's constant, and this part goes with Avogadro's number. So when you see this in the notes from the last time we had class, just fix it. It should be 6.626 times 10 to the negative 34. And not this weird Frankenstein stuff that I came up with. In the end, you get a wavelength in meters. So H is in joules seconds. And then to be able to get the units to cancel properly, you have to know that a joule is equal to a kilogram meter squared per second squared. So that's what a joule is. Yes, exactly. The denominator is the momentum because it's mass times speed. Exactly. And what he's saying with this equation is that the bigger the momentum, the smaller the wavelength. So it's saying with something as small as an electron, if an electron is like 10 to the negative 35 or something, then the wavelength is something comparable. And if it's something comparable, you would notice wave-like behavior. But if you put in the momentum of me or the momentum of you, then the wavelength's teeny tiny compared to the size of us. So that's why you see everybody as waves. And I mean, it sounds good when you say it fast. And that's what they go with in science. But to me, it still seems crazy. That doesn't mean it's not that it works. It just means that when I think about it, I think, well, I live in reality. And in reality, I don't think people are waves. But the math definitely works. And scientists believe that people behave as waves and things like that, depending on whether or not they look at the equation and they're like, yeah, that works, or they look at the equation and go, well, mathematically it works. So sometimes I look at the equations and the ideas they have in science, and I'm like, what? Were they drunk when they came up with that? But it's just science sometimes. And sometimes, yes, they were. So, like he was saying, momentum is mass times velocity, or speed. They are math. Yeah. I wish you hadn't taken that here. So, if you increase the momentum is designated with a rho, looks like a kind of almost a P. The smaller the wavelength. Or if you decrease momentum, the wavelength increases. So again, the formula for the de Broglie wavelength is h over, how can I get it that fast? Momentum, gosh. Okay, there we go, thank you. H over mu, so that's the de Broglie wavelength. All right, let me go switch back. Should have just go back one page. Go back one page? Back forward one page? Oh, that's good. Okay, sorry, I'm working out. I'm working too hard on my computer while I'm working on that. Okay, so let's work a practice problem. All right, so does anybody need a second to copy down this formula? All right, so let's work a practice problem. Let's say you want to find the de Broglie wavelength of 142 gram baseball. And this is the sample problem that's in the textbook. And they say that the velocity, which in this textbook is u, is 44 meters per second. And the ball has a diameter of 7.35 centimeters, and it wants to compare the wavelength to the diameter of the baseball. And when you look at problems like this, sometimes they will give you information you don't always need for the math part. Like, for example, the diameter doesn't come into the math at all. It's just something to compare it to in the end. So looking at the de Broglie wavelength, we've got this equals h over, and the mass has to be in kilograms. So to get it in kilograms, you divide by 1,000. So it's 142 grams, 1,000 grams, one kilogram. And so that's going to be 0.142 kilograms. All right. Yeah, with the diameter, it seems almost like you got to do some sort of a cylinder or sphere problem or something like that. Because normally when they give you diameter, that's kind of what they expect. But in this case, it's useless information until the very last step. All right, so the mass is 0.142 kilograms, and the velocity is 44 meters per second. And then instead of the letter h, I'm going to do 6.626 times 10 to the negative 34 joule seconds. Now let's take a look at the units. The units are joule seconds divided by kilograms meters per second. Now obviously hardly anything will cancel out as long as you have the joules in there. So you have to remember that 1 joule is equal to a kilogram meter squared per second squared. So you got to kind of plug that in. So kilogram meter squared per second squared. So this part right here is the joules, and then this part is just the second from right there. So it's joule seconds over kilograms meters per second. So this second will cancel out one of those. So when you have kilogram meter squared per second, the kilograms cancel each other. And then if we look at what's left, we have meters squared over seconds divided by meters per second. And meters squared per second then is equal to, when you do division with fractions, just flip the one on the right. That becomes seconds over meters. Right. So then you end up with meters in the end. So that's just, if you're looking at this and you're kind of wondering, where on earth are you getting meters from that? That's, you have to switch out the joules. And with it being kilograms, meters squared per second squared, that's why you have to have the mass in kilograms. Because if it's in grams, then you end up with some weird answer in the end. All right, so when you put it in your calculator, don't forget to use parentheses around the Heisenberg uncertainty principle. And then just put parentheses around parentheses 2. And then the answer you get, awesome. And we've got that right there, 1.06 times 10 to the negative 34 meters. So that would be 0.00000, etc., until you get 33 zeros and then 106. So they want you to compare that to 7.35 centimeters, which is the same as 0.0735 meters. So how big is the wavelength, which is this, that we calculated, compared to the diameter, which they gave us in the problem, which is that? Are they about the same size, or is one way smaller than the other one? Yeah, one is way smaller. The wavelength is way smaller. So what they're saying is that the baseball behaves as a wave, but you don't see that with your eyes because the wave is so very tiny. Would the wavelengths change since the ball is rotating? We're just calculating for baseball flying through the air. Yeah, we're calculating for baseball flying through the air with no rotation. So when it rotates and things like that, we change the momentum. And if it changes the momentum, then that would change the wavelength. But even if it changed the wavelength, it would not change it much, and the wavelength would still be itty bitty. So it would be very small. Does anybody need a second to copy any of this down? You just put a D in the chat when you get finished. D for like. Still can't seem to understand how an object can be compared to wavelength. Me neither. It works mathematically. What they're doing with this math is they're saying, well, it fits for an electron very well and shows why an electron would behave like a wave in that narrow slit experiment. But if it works for an electron, well, why wouldn't it work for a person? And then people that have seen people are like, that guy's not a wave, he's a person. He's like an object. And so they said, well, the reason is because the guy's so much bigger than his wavelength, but you just wouldn't be able to tell. Which, to some degree, sounds like they're, I don't know, grasping at straws. But basically what I would say is that mathematically you can show that a baseball behaves like a wave. Reality may be a different story. It's kind of like the difference between classical mechanics, which is Newtonian physics. So the things like gravity and somebody else come up with some sort of a Newtonian physics kind of thing, classical physics. Kind of like the idea that if you stop, or if you change directions, first you have to stop. So there's one set of physics that's all based on Newton's ideas, and then there's another one that is like mind-bendingly weird, and that's quantum mechanics. Exactly, an object in motion tends to stay in motion. Yeah. And so it's just kind of strange. Quantum is bizarre, to say the least. I read a book on it one time because I went to one of my professors and was like, this is crazy. And I don't understand where they're getting these crazy ideas from. So he loaned me a book and I read it. And the book in the end ended in string theory. So string theory is a bizarre idea that if there's a choice, both choices are made and two new universes exist from that, and then the next time there's a choice, you get a split and there are more universes, which, I mean, that's crazy. So some ideas in quantum are kind of out there. Other ones that work okay when you apply them to electrons. When you start to apply them to larger things, classical mechanics tends to work better. All right, so let's go and take a look at waves now and just get some information about waves in general. So let's say you have a wave. They used the example of a violin, and they said on one end of the violin, the string is clasped, and the other one is grasped. So it's grasped on both ends. And so when you pluck the string, then what happens is you get, I mean, you won't see that exaggerated of a wave, but the string will make a wave, and then you get sound waves coming off of that. When you see this kind of a wave where the ends are fixed, that's called a standing wave. It's the kind of waves you generally think of when you think about if you had a rope and made a wave out of a rope, or if you had sound waves, you're thinking about sound waves, they kind of tend to look like this. So looking at a standing wave, not necessarily a violin string, but a standing wave, we're just going to call this a standing wave now. There's always a 0 point, and so the wave will go up a certain amount, and will go down a certain amount, and then come back, and then do the same thing again and again. The places at the 0 point are called nodes. So everywhere there's a node, it's at 0 point. And then for a standing wave, think of this equation that the length is equal to the wavelength of the wave divided by 2. So it would kind of like be saying, all right, so we've got a wave. The wavelength is from here to here. And if you take the distance, then the length of the string is half the wavelength. It starts to kind of get a little strange. What they're trying to lead into is the idea of harmonics. And harmonics is just kind of telling you where it is you can have an actual wave. As they switch over to L equals N, lambda over 2. And N has to be, let's see, would there be another node in the top picture? Yeah, there would be one right here. That is correct. In this case, when you're talking about standing waves, N has to be an integer. A positive whole integer. When you get something that's like half, like 2.5 or something like that, then that math kind of goes nowhere there. And that's where they bring in circular waves, which is what de Broglie said the electrons do around the nucleus. So you've got the nucleus, and then you've got this kind of electron doing this wave thing around the nucleus there. That's a good question. This is really the formula. This one right here is assuming that n equals 1. So it's this one right here. The z, it's a 2. Sorry. Oh, it keeps changing itself into a z. Did you see that? Okay, now it's a 2. All right. No, it's my handwriting. That is not your bad. That would be mine. Okay. So looking at the circumference of a circular wave, if you have n lambda, that is equal to the circumference of a circular wave. Which is basically the same thing that they were saying before. Before they were talking about the length, and then now they're talking about the circumference, which is just a circular length. Oh, that's cool. In order for a standing wave to... I'm trying to think of a good way to put this. Okay, I'm good. Okay. So, looking at n, if n is not a positive integer, because it should be a positive integer, if n is not a positive integer, then the wave is unstable. It's discontinuous. In other words, it doesn't just go up, down, up, down, up, down. It's like up, down, you know, kind of a screwed up wave. And so this is where they're trying to explain from this that if you have a nucleus, it has protons and neutrons, which would make it positive, and you have an electron, which is negative, how come the negative electron doesn't just go and stick to the positive proton? Why doesn't it just crash into the nucleus? And the reason is, according to de Broglie, that the electron is moving in a wave around the nucleus instead of in a straight circular orbit. And if it's a circular wave, then the distance from here to here has to be a whole number integer. So it starts at n equals 1, and then goes to n equals 2, n equals 3, and so forth. So the whole idea there is they're trying to explain the electron will not crash into the nucleus because the electron moves in a wave pattern around the nucleus. And that's the explanation they give there. And if it seems kind of confusing, that's okay. It is a little weird. It's just you want to understand that the electron's not going to crash into the nucleus. Yeah, I know, it kind of gets out there. Quantum is bizarre, to say the least. But we will be moving past quantum before too long and then getting into some normal math and stuff again. So don't give up just yet. See how they thought of that? Heisenberg actually, I got a little quote from him at the end, which I think is kind of funny. He and de Broglie used to argue, and after a big argument, like Heisenberg went on a walk, and then he was like, basically asking himself over and over again, how come this stuff could possibly be real? It doesn't even make sense. So, well, I'll give you that quote in a couple minutes. Okay, so the Heisenberg uncertainty principle. Let's see. Oh, wait, no, we've got a couple more minutes. We've got like 5 minutes left. Okay. So the Heisenberg uncertainty principle says that the more you know about the location of an electron, so if I know a lot about the location of the electron, I know very little about its velocity. You could also say that since its mass times velocity is momentum, the more I know about the location, the less I know about the momentum. Location and momentum are called complementary properties. Complementary properties just mean that the more you know about one, the less you know about the other. So you kind of have to get to where you're at a happy medium. With a baseball, if you take a baseball and you throw the baseball, you have a pretty good idea the whole time where the baseball is. If you have a camera that's fast enough to take a picture, that'll catch the baseball in midair. And you know where it was, and then if somebody over here is measuring the speed, then you can get the speed and the location at the same time. But an electron is tiny, and you're not able to know as much. And so it gives the idea of probability of where you might find the electron. So they have this formula for the Heisenberg uncertainty principle. They have delta x, m, delta u. This is the uncertainty in the position. And so what that means is if the electron could be from here to here, but you don't know exactly where in there it could be, the distance from here to here is equal to delta x. And this is the uncertainty in velocity, or speed. And that stuff is greater than h over 4 pi.
Are you going to be back up there? Yeah, in a couple minutes. Yeah, you're going to have to sit in the sun.
So let's do an example problem with this. And we'll do it with a baseball to kind of explain why it is you know where the baseball is. We'll kind of compare it to an electron, and you'll be able to see why it is you don't know where the electron is. Does anybody need a second on this slide? No? Okay, we got 2 whole minutes, so I'm going to try to be kind of quick with this. Keep in mind, I have extended your homework due date to next Tuesday instead of this Sunday because I want to put more information online for you guys so that when you get ready to do your homework, it's making sense and not like, what? So, okay, so it's 3-1 to 3-5 in Smart Work. So 3-1, 3-2, 3-3, 3-4, 3-5. So all the sections we covered this week, plus adaptive 3A. So those are all due. All right, and so we got 1 minute, so I'm just going to write this down really quickly. You can take a look in the textbook and see this example worked out. But a baseball has an uncertainty of 6.80 times 10 to the negative 7 meters. And then when you calculate for the uncertainty in speed, so this is delta x, this is delta u, the uncertainty in speed is 5.46 times 10 to the negative 28 meters per second. So what they're saying here is there's a very small area where you're like, I'm not exactly sure where the baseball is. And here's another one, I'm not exactly sure how fast the baseball's going. But when you compare them to the size of the baseball, they're so small that you can say, well, I know where the baseball is, I know how fast it's going. But when you look at the electron and you do the same thing, the electron's size is similar to delta x and delta u, and that's why you're going to have more trouble, because if you have something that has an uncertainty of here to here, and the size of it is like this, or the size of it is like this, you pretty well know where it is. But if you have something that has an uncertainty between here and here, and it's like tiny, you really kind of don't know where it is. So that's the whole idea there. All right, so if you've got to go, I understand. I promised you a quote at the end. And so here's the quote. Heisenberg and de Broglie got into an argument. It was so heated, Heisenberg had to go for a walk, which is hysterical. You get that passionate about science. I mean, it's good, but kind of, I can't see me get into a heated argument about it. But he went on his walk, and this is what he said to himself over and over as he went for his walk. In nature, possibly be as it seems. In other words, the math is showing that it behaves differently. But does it behave differently? So he's like going for a walk, going, can this even be real? Does this even make sense? So I thought that was kind of funny. So, yeah. Because when I looked at quantum, this is kind of the thing that I've been asking. Math was a mistake. Sometimes I would agree with you. All right. Conceptual thinking, yes. There's a whole bunch of different concepts. The problem is they've never seen an electron. They've just detected them. They've studied them, but they don't really know much about them. Kind of like before when they thought the atom was indivisible. And then they found out it was divisible. They're like, what's inside of it? So that kind of thing. All right. So have a good weekend. Office hours are canceled for today because I have a huge project I've got to work on. Say, will you tell us the formulas needed? Yes, I will let you know the ones you have to know for the test. Absolutely. Yes, imaginary numbers. Imaginary numbers just made me mad. I learned about them. You have a nice weekend too. You may email me anytime you like.